we can now use our knowledge of the new symbol bottom to introduce the inference rules negation introduction and negation elimination. Now, negation elimination really is identical to bottom introduction. So the idea is that if you have shown that A and you have shown that not A for any sentence A, you can infer bottom. And as before, this makes sense given that bottom is simply shorthand for a contradiction such as A and not A. And as we discussed before, formally this rule looks like this. Suppose in line M you have the sentence A and in line N you have the sentence not A. You can then infer bottom and justify this inference by citing bottom introduction as applied to lines M and N. Now, why do we have two names for this rule? Well, the basic reason for this is that there's a justification or a kind of a thought behind the name for the rules. So the introduction rule for a connective always tells us how we can infer a sentence that has that connective as its main connective. So the rule bottom introduction tells us how we can infer bottom. And the elimination rule for a connective tells us what we can infer from a sentence that has that connective as its main connective. So negation elimination tells us what we can infer from a sentence whose main connective is the negation operator. And now it just so happens that these two rules coincide. So we can introduce bottom and justify this inference by means of bottom introduction, just in case we can infer something from a sentence whose main connective is the negation operator. So yeah, in this particular case, the introduction rule for the bottom sign simply coincides with the elimination rule for the negation sign, and that's why this rule has two names. So here are a few examples. They may look familiar. They are simply the examples that we have already seen when discussing the rule bottom introduction. And the only thing I've done here is I've switched out the justification for the rule. So we have seen that if in line M of your proof, you have established that if A then B, and in line N of your proof, you have established the negation of this sentence, you can infer bottom. And now we know that we can justify this rule by citing negation elimination. And similarly for all the other examples, whenever you have a sentence in one line of your proof and the negation of that very same sentence in another line of your proof, you can infer bottom and justify that inference citing negation elimination, or alternatively, bottom introduction. Now, negation introduction is a little more complicated. The basic idea is that if under the supposition that A contradiction follows, then you can infer not A. And so the thought is that a contradiction is never true. There are no contradictions. And so if A entails a contradiction, that means that A can't be true. Since it's entailment, the contradiction can't be true. So for example, if under the supposition that today is Monday, it follows that both today and is not Sunday, you can infer that today is not Monday. So formally, this rule looks like this. Suppose in line M of your proof you have a sentence of the form A, and this sentence entails a contradiction. You can then infer not A and justify this inference by citing negation introduction and the whole subproof from line M to N. Here are a few examples illustrating the use of this rule. Let's start in the top left corner. Suppose that if A then B then C. And suppose that this assumption leads to a contradiction. We can then infer that it is not the case that if A then B then C, and justify this inference by citing negation introduction and the subproof from N to N. Let's look at the second example in the bottom left corner. If under the assumption that it's not the case that A or C, it follows that a contradiction must be true, then we can infer that it is not the case that it is not the case that A or C. And cite negation introduction applied to lines m to n. To give you a third example, let's look at the top right corner. If the supposition that B and C, if and only if D, leads to a contradiction, you can infer that it is not the case that B and C, if and only if D. And to give you a final example, if the supposition that F and A and B leads to a contradiction, you can infer that it is not the case that F and A and B. And so on and so forth. Now, negation introduction is closely related to the rule indirect proof. You can think of them as mirror images of one another. What indirect proof tells you is that if the supposition that not A leads to a contradiction, you can infer A. And the reason here is that if the supposition that not A leads to a contradiction, then negation introduction would license us to infer not A. But not A obviously entails A. And so that means that if the supposition that not A leads to a contradiction, you can infer A. Formally speaking, it looks like this. If the supposition that not A leads to a contradiction, you can infer A, and justify this inference by citing indirect proof as applied to the subproof from line m to n in this example. So here are again a few examples illustrating the use of this rule. Let's start in the top left corner. If the supposition that it is not the case that if A then B then C leads to a contradiction, then you can infer that if A then B then C, and justify this inference by citing indirect proof as applied to the subproof from m to n. As a second example, let's look at the left bottom corner. If the supposition that it is not the case that A or C leads to a contradiction, then you can infer A or C, and justify this inference by citing indirect proof as applied to lines m to n. Furthermore, now let's look at the top right corner. If the supposition that it is not the case that B and C, if and only if D, leads to a contradiction, you can infer that B and C, if and only if D, and justify this by citing indirect proof as applied to the subproof. And our final example in the bottom right corner, if the supposition that it is not the case that F and A and B leads to a contradiction, then you can infer that it must be the case that F and A and B, and justify this by citing indirect proof as applied to this entire subproof. This proof is going to illustrate two things. I'm going to illustrate the two negation rules, negation introduction and elimination, and I'm going to illustrate how to construct a proof from no premises. So here we want to prove a conditional. We want to prove that if it is not the case that if P then Q, then not Q. So the antecedent of the conditional that we want to prove is this negated conditional here. The antecedent is that it's not the case that if P then Q. And the consequent of the conditional that we want to prove is not Q. And now we want to show that this sentence follows from no premises whatsoever. In other words, we do not have to make any additional assumptions in order to prove this sentence. So you can see at the top of my proof, I do not have a Fitch bar, given that we do not have any assumptions. Now, how can we prove this from no premises? Well, the main connective is a conditional, and that suggests to me that we can prove this using conditional introduction. Now, conditional introduction requires me to set up a subproof. And now this subproof is going to introduce an assumption into our proof. I am going to assume the antecedent of our conditional. It's not the case that if P then Q. And I want to show that this assumption, that it's not the case that if P and Q, leads to the conclusion that not Q. And if indeed I can show this, I can then infer our desired conclusion, citing conditional introduction and the subproof from 1 to somewhere, question mark. I'm also going to put a question mark here to remind myself that this is on my wish list, that I have not yet proven not Q. Okay, so this is the basic setup of the proof. Now the question is, how can I establish that not Q? Well, the main connective here is the negation sign. So that gives me an idea. I'm thinking, well, if this is a negated sentence, I can probably prove it using negation introduction. And negation introduction, again, requires the use of a subproof. So negation introduction goes like this. If the assumption that Q leads to a contradiction, then I can infer not Q, citing the rule negation introduction and our subproof from 2 to somewhere. Okay, so how can I establish a contradiction here? How can I show that the assumption that Q leads to a contradiction? Well, let's look at the first line of our proof. The first line tells me that it's not the case that if P then Q. But I also know that the conditional if P then Q is true whenever Q is true. So that means that if I assume Q, I should be able to prove that if P then Q. And this would contradict the first line in my proof, allowing me to infer bottom. So this is the proof strategy. I want to prove the conditional if P then Q, and I can then infer bottom, citing bottom introduction and lines 1 and question mark. Okay, so now the question is, how can I prove this conditional if P then Q? Well, the main connective is a conditional, suggesting to me that I can prove this using conditional introduction. And conditional introduction requires me to set up a subproof where the basic idea is that if under the supposition that P, I can infer Q, then conditional introduction allows me to infer if P then Q, citing the subproof from 3 to somewhere. Okay. So that's our proof at this point. Our next question is, how can we establish Q? We have not yet actually proven Q. Well, if we look carefully, we see that we do have Q in line 2 of our proof. And that means that I can simply reiterate Q in line 4 of the proof. So I am going to justify this inference of Q, citing the rule reiteration applied to line 2. And now I can infer if P then Q, citing the rule conditional introduction and lines 3 to 4, And I can go on to infer bottom, citing bottom introduction and lines 1 and 5. And I can infer not Q, citing negation introduction and lines 2 to 6. And finally, I can infer the conditional that if it's not the case that if P then Q, then not Q, citing conditional introduction and the subproof from line 1 to 7. Okay, this completes our proof. In today's lecture, we have learned introduction and elimination rules for each of our 5 connectives. And we have furthermore learned introduction and elimination rules for the new symbol bottom. And we have seen a few examples of how to construct Fitch-style proofs. In the next lecture, we are going to go on to discuss proof strategies that are going to help you to develop complex proofs on your own.